In this next section, we're going to go through system of linear equations in two variables. So we're going to start out with defining what a linear system is. Then we're going to go through two different methods, the first one being substitution, the second one being the elimination method. Okay. So when we're talking about a system of linear equations, all it means is you're going to have possibly 2, 3, however many lines, and we're trying to see, is there some xy value that is going to satisfy both equations? There might be one, there might not be one, or there might be multiple. Really, there's three possibilities as to what could happen. So if you think of your two lines, you have one line maybe here. One possibility is those two lines do intersect in a single point. So there's one point that satisfies both lines. In this case, we're going to have one solution to our system. A second possibility, though, is we dealt with lines, and one of the properties was that they could be parallel. So in this case, the two lines are going to run next to each other. They will never cross. And because of that, there's going to be no solution to our system of equations. So we're going to have parallel lines potentially. So there will never be a single point that satisfies both of the lines simultaneously. When this happens, we have something that's called an inconsistent system. And then our last case is maybe we have a line here. One possibility is that the other line is really just going to lie directly on top. So in this case, they're going to be the same lines. Okay. When that happens, every single point is going to be a solution. So if it's on one line, it's definitely going to be on the other. So in this case, we have infinite solutions. Okay. And just like the inconsistent system, this one gets a special name. This is called a dependent system. Okay. So before we start out with our two methods, let's do an example just to kind of familiarize ourselves and refresh on our graphing skills. We're going to solve the system by graphing. And so both of these are just two lines that are written in slope-intercept form. We can graph them. But the problem is graphing is not going to be very good for us, especially if we have a case where you have like decimals or fractions as your answer. So we can graph by hand, okay, but it's not going to be perfect. So we'll start with our first line. Here, our slope is -1 and our y-intercept is -5. So we'll go ahead and plot that point at -5, which is actually right here. I'm not great at counting. And then our slope is -1, so we go down 1 over 1. And that gives us another point. Down 1 over 1 gives us another point. Down 1 over 1 gives us another point. Okay. And I really want to find a bunch more, so I'm also going to go the other way. Let's go up 1 to the left, up 1 to the left, up 1 to the left, and that should be sufficient. So you can see, even just by graphing right here, my graph isn't super accurate, which is why this method is not always going to be the best. So that is our first line. This is y equals -x minus 5. Now if we go to the second line, our slope is 2 and our y-intercept is +1. So we're going to start by graphing that point, and then our slope being 2 means we go up 2 over 1. And we get another point right here. But I can already tell now if I continue going up this way, the intersection is going to be down here. So what I really want to do is I want to find points to the left. So I want to go down to over 1 instead to give us another point right here. Then I'm going to go down to over 1 again. And then we've actually hit the point where these two coincide. Okay. So this is our point that's going to be on both of the lines, which is the point -2, -3. So the graphs intersect here. At -2, -3. So this is the solution to our system. It is the point that satisfies both lines. Okay? But like I said, this is good in a pinch or if you're unsure what to do or you totally blank, but it's not great when we have fractions as answers, or it's not great in general if we're just kind of messy with graphing. So we want to go through 2 different ways to solve these systems, and our first one is going to be substitution. So they're all appropriately named methods. We're going to take one equation and we're going to substitute it into the other. So we really have a process that we're going to follow for both of these. So the very first step is I want to solve one equation for one variable, and you get to pick and choose. When I look at this top equation though, I can easily add that y to the other side and I'll have my value of x. So I'm going to work with that one. The first equation is x minus y equals 2. We go ahead and add y to the other side, and that tells us that x has to equal y plus 2. Okay. And then I'm going to go ahead and I'm going to put a little check mark next to this first equation to tell me that this is the one that I've dealt with. Now that I have that, I'm looking for an x and y that satisfy both of these. So this x from the first equation also has to be the x in that second equation. So our second step is we're going to substitute this expression into the other equation, and then we're going to solve for our remaining variable. So we have not dealt with the second equation at all, and then we figured out that x needs to equal y plus 2. So in this expression for x, I'm going to go ahead and put y plus 2 instead. And then we haven't dealt with either of these. Okay. And essentially what I've done now is I've created a single equation involving y that I can go ahead and solve. So just dropping those parentheses because we have nothing out front, we have y plus 2 plus y is equal to -2. Combining those like terms gives us 2y plus 2 equals -2. Okay. And then we solve our equation as we did before. We subtract 2 from both sides. We're going to go up here. And that gives us 2y is equal to -4. And then last but not least, we go ahead and divide by 2. And that gives us y equals -2. So we've now figured out what the y value has to be that satisfies our system. So in theory now we've used both of these equations. So I have the y value. The only other thing we need is to figure out what the x value is. And that's where our substitution comes into hand, because x is equal to y plus 2. Something else you can do is you can really just plug that y value back into either of these equations and you go ahead and solve for x. But again, total preference as to what you want to do. So our third step is now to use this value back in step 1 to find that remaining variable. So we were able to figure out that x was equal to y plus 2. we just figured out that y has to equal -2. So the x value needs to equal -2 plus 2. So our x is going to equal 0. So at this point, we have our solution. You can write this a couple different ways. You can say x is equal to 0, y is equal to -2, or you can write that as the coordinate pair that satisfies both of the systems. One thing we should get in a habit of doing, especially in these kind of circumstances, is if you have time, definitely check that your solution actually works. So we want to check that it does satisfy both equations. And this will just verify we haven't made a mistake. So our first equation was x minus y equals 2. If I plug in our values, x is 0, y is -2. I really should get something that's a true statement. So when I have that minus minus, turns into a plus. We get 0 plus 2 is 2, which indeed gives us a real point on the line. And then if I do the same thing with the second equation, x is 0, y is -2, we indeed get a true statement. So really this point does satisfy both equations simultaneously. That is our solution to the system. Let's try another one of these. We're going to solve the following system: 3x minus y equals 2, 3x minus y equals 4. So our very first step is I want to take one of these equations and solve for a variable. Here, probably y is going to be the easier one because I really don't want to deal with dividing by that 3 in front of the x. So we're going to start with this equation. So we've got 3x minus y equals 2. We'll go ahead and subtract the 3x from both sides. And that leaves us with -y is -3x plus 2. And then we need to get rid of that minus sign. So really, I'm just changing the sign on everything, just the same as dividing by -1. So we get y equals 3x minus 2. Now, I want to plug this into y in the second equation. So we have not touched that one yet. We have 3x minus y equals 4. And our y, we're going to replace by 3x minus 2. So we have 3x minus this expression equals 4. And so I've got a single equation now involving x. We go ahead and distribute that minus sign. So it has to change everything in the parentheses. But in doing so, these 3x's cancel each other out, and we end up with 2 equals 4. Okay. So this is that case where I end up with something that doesn't make sense. This is never a true statement. So when this happens, we're going to have no solution to our system. And really, you can kind of look back up here. The very first line tells me 3x minus y equals 2. I have exactly the same expression here, but it equals 4. So they have the same thing on the left-hand side, but different right-hand sides. There's never going to be something that makes these two equal to each other. So this is that case. They're going to run parallel if you put them in slope-intercept form, but they're never going to intersect. So anytime you end up with something that is a false statement, this is our case of no solution. So all we have left, we're going to now go through our second method to solve these, which is elimination. Now really your homework is going to say solve it using this method. Your test even might say that. In reality, just kind of do whatever comes first to you, whatever you think might be the best. Like this example we did back up here is actually perfect for elimination, so it's set up for us. So you want to do what your gut tells you to do. So our goal with the elimination method is we want to add these equations together and cause one variable to eliminate. So if I have one value being like 10x and the other equation being negative 10x, if I go ahead and add those together, they're going to cancel. So looking at these values, we have a positive y and a negative y. If I can make those the same number out front, then when I add them together, they'll disappear. So the very first step is you're going to multiply one equation, or potentially both, by a number, so that one variable will cancel when the equations are added together. So I'm going to start just by rewriting my equations down here. And again, you have a couple different ways you can do this, because I could take my top equation, multiply it by positive 3, and this by negative 4, and that would make our x values cancel. But since these already have opposite signs, I'm going to work with those. So if I take this first equation and I go ahead and multiply it by 5, and this bottom equation by 2, I come up with the system for the first one being 20x plus 10y equaling 70. And then the second equation is 6x minus 10y equals negative 44. So we now have the same value in front of y, but opposite in signs. So our second step is we're going to add these equations together to eliminate one variable, and then you're going to solve the resulting equation. So rewriting our 20x plus 10y equals 70, and 6x minus 10y equaling negative 44. We go ahead and add these together, so our 10y's cancel. And 20x plus 6x gives us 26x. 70 minus 44 gives us 26. So really, we just need to solve 26x equals 26. And then by dividing by 26, we find out that our x value must equal 1. So I figured out one value in my equation. Now I need to figure out the remaining one, so I can go back really to either of these equations, plug in that x needs to equal 1, and find my missing y value. So I'm going to go ahead and use the first equation we were given, 4x plus 2y equals 14, and we know that x has to equal 1. So plugging that in, that gives us 4 times 1 plus 2y equals 14, which is just 4 plus 2y equals 14. So we go ahead and subtract 4 from both sides, gives us 2y is 10, and then we divide by 2 and find out that y must equal 5. So our solution is that x equals 1, y equals 5, or again, you can write it as the 0.15. So we've got one more example that we're going to do, and again, we'll use elimination, but we just want to solve the system. So we're already set up again. I have a positive and negative p-value. So if I can get them to be the same number out front, we're in business. We can go ahead and eliminate those p's. So luckily, I only have to multiply a single equation here. If I multiply by 2, that's going to make it so that there is negative 6p, and they're going to be able to eliminate. So So rewriting our system, our new first equation is negative 6p plus 2q equals negative 12. And then we have positive 6p minus 2q equals positive 12. And now if we go ahead and add these together, the p's cancel, but also the q's and also the negative 12s. So you end up with nothing on the left-hand side and nothing on the right-hand side. So in the contrast to the case that we ended up with something that was always a false statement, this is always going to be true. So this is our case where they happen to be exactly the same line, because really one is just double the other. So there are infinite solutions here. But we don't want to just say there's infinite solutions, because not every single thing is going to work. Really, there's still just certain P and Q values because they have to be a point on the line. So we have a certain way that we need to express this, and we're going to write our answer in set builder notation. This is also called parametric notation. It's got a couple different things. So what I'm going to do is I'm going to first write what that notation is going to look like, and then I'll dissect it piece by piece. So really, we have a solution set as our answers. They are P and Q values. We're going to put a semicolon, and then I'm going to go ahead and put my equation here that needs to be satisfied. So the way we actually read this is, again, those braces indicate that this is the set of P and Q values, so all points P and Q. The colon means such that. And then this last piece is whatever conditions you need to hold. So it is the set of points P and Q such that this equation is satisfied. Okay. So it's still restricted to just points that are on the line. You might also need to potentially rewrite that equation. So if I work with this first one, that's negative 3p plus q equals negative 6. You can add 3p to both sides to say our q value is negative 6 plus 3p. So something else you could do instead of this equation is put that your q value must equal negative 6 plus 3p. So a second way to write this is you can pick your p to be whatever you want, but your q value has to satisfy this equation. And then we say p is any real number. So this is our parametric form to indicate that these are all of the points on the line. Typically what you're going to do is this one in your homework, but it might also ask you for this form.